different. One should not mix it. These are the two different issues, and one has to understand from the broader perspective of the whole issue together. Okay. Acha. Now we started talking about in the last class the spin state configuration and electronic structural aspects by using variety of techniques including EPR. What I have been repeatedly telling all of you that EPR is not a technique by which you can derive everything as far as the electronic structure is concerned alone. You need to take EPR in combination with theoretical calculations and variety of other techniques together. Then you can have a better perception about the electronic structure. Okay, but EPR is one of the important techniques by which you can get a broader picture. Okay, and when you talk about the electronic structure, already I conveyed to you in last class that that is more difficult when both metal and ligand, they can have more than one particular oxidation state or variable oxidation states. I said most of the ligands having in organic chemistry or organometallic chemistry, what we follow, most of the ligands, they do have a single redox state or oxidation state, whichever way you want to specify. And in that case, only the metal oxidation state could vary depending on variety of parameters. So it's a simple case. But there are selective cases where the ligands can also exhibit more than one oxidation states, and that is available in our biological system as well. Okay. So one example we have picked up, that is the quinone example. And there we have shown that quinone can have either cis-quinone or paraquinone, whatever you consider. The cis-quinone, we know that they can have three oxidation states like this. And they have, when they bind to the metal ion, that CX bond distance, which is diagnostic to its oxidation state, and I have given you the table. And once you have the crystal structure, you can get the information that in which oxidation state your ligand is there, and then subsequently metal and other things. Okay. So, and then we had taken three compounds, and there we have explained that two issues are there. One is the native state. Native state means the compound what you isolate. Okay, in a solid state, in a bulk material. And there you could grow the single crystal. And once you have the crystal parameters, particularly the bond metric parameters, you can propose the oxidation state of the redox active or non-innocent ligands, and then you can figure it out the electronic structural configuration at the metal ligand interface, where other ligands are actually not redox active. And then the second question arises that what happened during the electron transfer. So we have described that it is nothing one-dimensional. If it happens to one set of compounds, the similar thing would happen to the other or analogous set of compounds. No. You have to study each and every compound differently because of the fact everything depends on the energy configuration of the metal and that particular redox active ligands, the frontier orbital energy configurations. So if slightly varies here and there, then your whole parameters would be changed. Then we have shown that this particular case, that one electron oxidation or electron reduction takes place at the ligand site. Okay, that could be understood quite well by using the EPR. On the other hand, this particular case, we have established that EPR could tell us that electron transfer, oxidation, or reductions both are taking place at the metal site, not at the ligand site. So EPR could nicely explain the site of electron transfer. That also tells us the electronic configuration at the metal ligand interface for the redox state, like the native state. Because redox states, that the problem is, in most cases you cannot generate the crystal because you have to study in solution of the, right? Okay. Then we move for one unique case where there are two examples we talked about, and we said very clearly that the crystal, these are the native states. So crystal structures are available. So looking at the bond parameters, Cx parameters, it can be easily concluded that these are in the they are in the radical state, and if so, and then composition one could easily determine 2 minus, no charge outside. So naturally, your copper oxidation state would be copper 2 by means of simple arithmetics. And if so, both the compounds are essentially 3-electron system, right? 2 electron on the ligand and 1 electron on the copper side. Now the spin interaction, that is very important. Now both the compounds, if you look at little bit carefully, slight differences are there, but here it is absolutely, tetra-coordinated. There is, but here it is a pseudo-octahedral situation, though it is weak, but still pseudo-octahedral situation. And as a result, if we see the EPR of this compound and this compound are completely different, or I should say diagonally opposite. The EPR suggests this is a metal-based EPR, copper-based EPR, but here it is a ligand-based EPR. That means the quinone-based or iminoquinone-based EPR here. So why it is so? That could be understood very easily, but based on the fact of the location of the unpaired electron on the copper center, and we have been noticing over here, this is Z out configuration, but this is Z in configuration. So we know the location of the unpaired electron in which orbital it is being located, and then accordingly, since the ligand electron at the pz level, so this coupling is not possible, and because of the twisting nature of this molecule, the two ligands are a bit twisted. As a result, magnetically, these two pz orbitals, they are coming within the interacting distance, so that interaction takes place effectively compared to 1-2 interactions, what is being observed over here. Because here, both the ligands and the metal orbitals carrying the unpaired electron is essentially same, g orbitals. So parallel coupling between 1 and 2 is likely, remaining the unspare spin in one of the ligands, and as a result, ligand-based EPR. Okay. Now, this EPR is such a powerful technique. Once you understand the technique well, you could derive variety of transformations, both at organic level as well as at inorganic level, of course. In organic level, it is rather easy. In inorganic level, it is rather complex, right? Now, if you see the organic reactions, as you know that most of the transformation, either it follows through the radical pathway or non-radical nucleophilic pathway. Now, you may have different kinds of, what I should say, uh, indirect evidences. Okay, but EPR would provide you very direct evidence in favor of the radical pathway in the organic transformation. If you could trap the intermediate, it's not easy to trap the intermediate, because if it is a radical, the reaction rate would be very fast. But there are ways to trap the radicals. I'm talking about the intermediate radicals, and then you can, extend the direct evidence in favor of your mechanism that it is not nucleophilic, rather it is radical mechanism. Okay. Now, in inorganic wise, there are ample of examples available in the literature. I just thought to take one particular example to highlight two issues parallelly. But this example would tell us two issues parallelly. Okay, what are those two issues? For example, if you start from this particular compound, what we call, you can say is a beta diketominate, and this L is acetylacetone. Acetylacetone is the redox non-inactive ligand. So it just, it function as a silent spectator. It just completes the, octahedral ligand framework. That's it. So otherwise, it has of no role. But this particular ligand, which is called beta diketominate. Now, this beta diketominate is interesting ligand. That is a redox active ligand. That means it can exhibit normally in an anionic form, or it could also exhibit in a radical form. Both are possible. Okay. Now, that is not possible in a free ligand system. Free ligand is just anionic or protonated. If it is a protonated, that is neutral. If you remove one proton, then it will become anionic, right? This is how beta diketominate. Now, this particular compound, here it is 1 minus, and 2 ACAC means 2 minus, metal in +3 state, and there is no charge. So, electrically neutral compound. Now, this compound is very interesting, that if you allow it to be exposed in atmospheric condition, it activates the molecular oxygen, and oxygenation takes place. That means beta diketominate getting converted to ketodiimine. Okay, so our concern is not the transformation. Okay, our concern is how EPR would help us to understand the mechanistic aspects of this particular transformation. Okay, now this is a well-established mechanism. So from EPR perspective, I would like to share with you. For example, you know the molecular oxygen is a triplet, so it can only react with the triplet. Okay, or react not triplet, react with the system having open cell configuration. That means unpaired electron is there. In this compound, that metal is having unpaired electron. Okay, it might have attacked at the metal site, that is possible, and it can attack over here. But all experimental fact it established know that it does not attack at the metal site because of the fact it is already 6 coordinated. If it attacks to the metal as an intermediate, then it would become 7 coordinated, which is not a likely situation. Okay, it has been established. So it could attack at the C site, the C beta site. Now, if you look at this particular electronic form of the compound, one could consider Ru3 minus, okay, anionic ligand. But since we know that this is the redox active ligand, alternate possibility one could imagine the intramolecular electron transfer. That means one electron may go from here to here. So one electron may move from here to here. As a result, metal would be reduced to 2, and here one radical would be formed. Now, what is the justification of considering the resonating or tautomeric form of like this? Because if you look at the EPR of this compound, and if you look at the G parameters, and I said the G parameters, if it is 100% metal based, then it should be 2.1 at least, if not more. But the G parameter suggests 2.06. Of course, it is metal based, but not 100%. That means the minority configuration of this 2 radical cannot be ruled out. Now, if oxygenation has to take place over here, naturally that molecular oxygen has to attack over here. And if it attacks over here, then it gives us the superoxo compound. And then superoxo gets converted by this proton abstraction to hydroperoxo, and subsequently the desired product. Now, if it is so, this is a very fast conversion from carbon radical. It cannot be trapped. So they could trap this one, this intermediate. Now, if you carefully look at this intermediate and the G anisotropy parameter, you see a 2.008, which justifies very strongly the consideration of superoxo, that radical-based intermediate in the system, which justifies that this reaction is following through the tautomeric form of this starting compound. So starting compound is found in solid state, but in solution it tautomerizes, develops a radical over here, and that radical reacts with the triplet oxygen and gives us the superoxo radical intermediate, and that intermediate could be tested quite well by EPR, and that EPR G parameter in comparison to the starting EPR G parameter, it can be convincingly, conveyed that this mechanism is perfectly correct. Now, if you go for another redox active ligand, now say nitrosyl. All of you must be aware of nitrosyl is so important in our biological system. Our whole neurosignaling processes are being controlled by the nitrosyl. Whole neurosignaling process, our blood pressure, everything is controlled by the NO. Now, NO is the poisonous gas, all of you know it. But in our biology, slightest amount of NO is there, and which is mandatory. Without that, we cannot survive. Our brain system won't work. Okay, so NO is very vital molecule for our biology. If there is NO deficiency, there are drugs available, you can inject it, all sort of issues are there. So if you are interested, you can go through the literature. I'm not talking about the details of this. What I'm trying to say, that it is a well-established fact that NO can have the 3 or even 4 redox states. So normal NO gas is a radical, only radical having no charge. Okay, neutral radical. Then NO plus, and then NO minus, and then NO dot 2 minus. That is isoelectronic to the superoxo and all sort of things. So I'll not touch upon this. Now you have a compound like this. Okay. Now, interestingly, we are talking about, remember, we are talking about electronic structural aspect now by EPR, right? So it's a kind of application. Now, if you look at this compound, there is one tridentate ligand, one bidentate ligand. And we are assuming both the ligands are neutral. If it is a neutral, this is 1:2 conducting. Now, if it is 1:2 conducting, and then what does it mean? Means the metal must be in the +2 state, because NO radical, which is having no charge, is a neutral radical. Already we know it. Since it's a neutral radical, so metal has to be in +2 state. That's why the charge is +2. There is no internal charge balancing over here. So you must have 2 perchlorate, 2 PF6, 2 some other anions, etc. Now, if you have a crystal structure of this molecule, you can easily tell whether it is NO dot or NO plus or NO minus. How do you tell from crystal structure? If it is NO dot or say NO plus, then nitrogen would be in sp hybridization state. So metal N oxygen would be linear, and the angle could be 180, close to 180. This angle, metal, nitrogen and oxygen, 180. If it is NO dot, N is the sp2 hybridization state. Or not really, if it is NO minus, it is 100% sp2. And then this angle would be 120. And if it is NO dot, then it will be somewhere in between. And normally NO dot angle is around 140. It's essentially sp1.x, that is in between sp and sp2. And moreover, that NO, then in this case it will be a triple bond. In this case it will be a double bond. In this case it will be somewhere. In this case it will be double bond. In this case in between triple and double. So what I am saying, if NO in the plus state, triple bond. Minus state, double bond. If it is NO dot, somewhere in between. So bond parameters can tell you. And the angle also close to 180 for linear NO plus. For this is absolutely bent, 120, and this is semi-bent, somewhere in between. So crystal tell you that what is the redox state of NO in your molecule. Okay, and then if it is NO dot, in this case it is so. And if you record the EPR, then this is not EPR active, T2G6. This is EPR active. So you should expect one line spectrum with the 3 splitting because of the nitrogen. Nitrogen hyperfine, you could have seen it. But what do you see? You see a kind of axial EPR. Right? This is the way the axial EPR looks like, right? And there you could see the nitrogen splitting, 1, 2, 3 splitting, this nitrogen splitting. Now, what does this axial EPR means? It means that this is the major configuration of this particular molecule, not necessarily 100% configuration. That is the delicate issue as far as the electronic structure is concerned. Okay, so this metal involvement in the EPR of this molecule could only be interpreted by the fact of its resonating electronic configuration instead of any precise electronic configuration, a single configuration. That means ideally it should be Ru2 NO dot, but you can expect to have some kind of internal electron transfer from here to here. As a result, it goes Ru2 to Ru1 and NO dot becomes NO plus. So what is happening? That intramolecular, you have not added a single electron or not withdrawn a single electron. So internal electron transfer between these two centers and their total barrier, this Frank-Kernam principle, all sort of thing, if you look at very close to each other, that is how the resulting form develops, right? Okay. So here, this is the EPR active site. Here, this is the EPR active site. Now, it could be back calculated that 90% configuration actually this one, and that's why it is mostly the ligand based. It's a spreaded EPR, mostly the ligand based signal with nitrogen based hyperfine with slight anisotropy, which has been originated because of the fact of T2G6 EG1, that Ru1 configuration, right? So this is how one could think about EPR. Helps us to understand the resonating configuration. In the previous case also I said, and your tautomeric form, all sort of things. Now look at one very complicated issue where EPR fails. It's not EPR is the God. It can solve everything. No. There are many complicated issues where EPR even fails. Now this is one example. As I said that NO can exhibit in different redox states in the previous slide. But here we have taken one particular molecule. This molecule is very well known from our lab point of view. This is a Browning compound, that testing. We know that. Now, there's 100 years debate. It is still going on, the debate. What is the debate? Debate is still going on, I am telling you. It started 1900 sometimes. And now this problem has not been sorted out. If you look at this molecule, here 5 water molecule, which is just filling up the coordination number. So not at all redox active. So there is no second configuration of water. Now NO can have the 3 configuration what you could imagine, right? This is a rare configuration, so you should not think about it. Now, so if we consider NO plus and the charge is 2 plus, right? Keeping the charge, overall charge, that's a fact, charge in mind, then we can think about iron 1 NO plus, and then iron 1 NO plus means 2 plus, then 2 plus. Or you can think about by intermolecular electron transfer, that from here to here. So here to here, iron 2 NO dot. And then this is 2, this is no charge, water no charge, 2 plus, no problem. Alternatively, we can think about again electron transfer from metal to NO, iron 3 NO minus, and iron 3 NO minus. So basically 1 could be balanced, then 2 plus, no problem. And NO minus, you know that NO configuration, pi star orbital, 1 unpaired electron for NO dot. And if you put the second electron, that is NO minus, which would remain parallel. Okay, NO minus with a spin pairing, it requires extra energy. Okay, so in most cases it will remain parallel. So it's a 2 unpaired electron is here. Now, if you look at the total electronic configuration for all the three cases, your S equal to 3 by 2 quartet molecule. Because of here iron 1, you see that D7 configuration, okay? And if you put it this way, then this is high spin configuration you have considered 3 by 2. This is high spin configuration iron 2 D6 NO dot. Okay, 1 unpaired electron is there. So 4 electron minus 1 unpaired electron on NO 3 by 2. Here high spin 5 for iron 3 and 2 for here. So essentially 3 unpaired electrons. In all the cases 3 unpaired electrons. So you can have 3 by 2. Or if you presume that it is low spin configuration, you can do so. Then you will be seeing again in all cases 1 unpaired electron each. If 1 unpaired electron and 3 unpaired electron does not matter, matter is that all the configurations having the same EPR features. If I consider quartet, if I consider, actually it is quartet. Okay, so all the three configuration gives you the same EPR. So EPR cannot distinguish it. But Mossberg can give some impression, not complete impression. Calculation, they're so energetically close to each other, even calculation fails. So that is how this problem is still alive. So last 100 years across the globe, people is trying to propose whether this is the right configuration or this is or this is. There are many. One group believes this is the configuration. Other group believes this is the configuration. Other group believes this is the configuration. Beliefs means not arbitrarily, based on the newer data they could accumulate. So certain data favors in one direction, and certain data favors in other direction. So that dichotomy is still persisting. Yeah.
Why is EPR same in all three cases? Because the number of unpaired electrons are certainly varying in all the three, right?
No, same. That is a 3 by 2. You look at the diagram, na? Number of this diagram contains only the metal, and then side by side the unpaired electron is also there, na? They would be coupled. The direct bond.
Okay, okay.
Clear, na?
Sure.
So I consider high spin. If you consider low spin, then you will be also saying half, half, half. Okay.
Okay, okay.
Okay.
And
So
why
that
is it anti-ferro, sir?
uh,
Why is it anti-ferromagnetically coupled?
why
Is
not?
it
Because these are the direct bond, na? So if you have 5 electrons here, you have 2 electrons here.
okay?
Okay. And they are so closely proximated, so they would certainly overlap. Okay. And as a
Okay,
result, you my 5 minus 2, so essentially 3. Okay. So
okay, okay.
magnetic moment of this compound is 3 by 2. Understood? So if you solid state magnetic moment or solution magnetic moment, if you measure, you will be getting magnetic moment for 3 unpaired electron. That is the fact. Okay. And compound doesn't show all the 3 configuration. No? Compound shows only one configuration. Question is, magnetically you cannot differentiate among these 3. So EPR wise, you cannot differentiate among these 3. Am I clear? So you can only, there are, they have done certain ESCA, they have done MOSBAR, they have done this, they have done that, what's not. So they could see that certain experimental data, if you put say 10 experimental data with the calculations together, certain data are in favor of one direction, certain data are in favor of other direction. That means something still is missing. And that is why 100 years, more than 100 years, everybody across the globe, those who are interested in this problem, they are trying to figure it out. Across the globe, I'm saying. So that is how the science grows. Okay, but here it is a static phenomena. Nothing moves, beyond a particular limit. So what I'm trying to convey that EPR also fails to help us to understand the electronic structural configuration in certain cases. This is one of the examples. There are many such examples are there in the literature. Now let us move into the last chapter where last part of our discussion.
Sir, the
Just like, yeah.
Sir, in the
Yeah.
case of the Brown ring complex, the bond parameter can resolve what is the actual.
Well, problem is, in inorganic chemistry, you have to understand two issues parallelly. One is the electronic configuration in solid state and in solution. Not there are cases where solid and solution they behave identically. Okay, so whatever you notice at the solid state, you can easily extrapolate it and you can prove it that the same similar configuration exhibits in solution as well. But there are numerous cases where what happened, the solid and solution they don't behave equally. Okay, this is the first way to put the answer. Second way, Browning, there is no structure actually. A lot of derivatives were there. Very recently, I think 2 years back, if you wish, I can share. One Angwantic chemistry paper has appeared. They are claiming that they have shot out the structure. Okay, so Browning compound, you can imagine that layer. Okay, so they are claiming they have sorted out, but I have gone through that paper. Well, they have given some impression, but it is not very conclusive. So that is another problem. So first problem is the structural evidences are not there conclusively. I'm talking about they have all derivatives are there. So derivatives and exact rounding, some differences are there. First point. So, and solution structure and solid structure not necessarily always be the same. So, solution structure wise, there is a huge ambiguity as of now. You just type rounding compound electronic configuration, you will be seeing thousands of paper, including some of our own paper. So what I'm trying to mean that there are occasions where these sort of complexities come up, and once it comes up, then we have to tell this is the present scenario. So we cannot take the problem up to this extent, and tomorrow someone may come up and also try to provide some better interpretations over there. Okay, so now like uh, you know everything it begins one day and everything must end another day, right? Unfortunately today it is the day when our this lecturing would be ending. So this is the last part of my whole discussions. I have how much of time? Let's see. Yeah, I have almost 40 minutes time still, right? Am I right? How much time I have in 20 minutes, right? Okay.
No, I thought
Now,
it's 40 minutes. No, it's still 3:30.
oh, it's 3:30. Okay. So now there is another topic which I thought to cover. It's a just ocean. Ocean means again the electronic structures, and electronic structure under the banner of mixed valency. Okay. Now mixed valency means, let me tell you, the concept of mixed valency it develops when you have a polynuclear setup, not in a mononuclear setup. Mononuclear setup, if you consider the valency only around the metal center, then mononuclear center does not come into the picture under the banner of mixed valency. So you have at least two metals. Now in a metal complex, the two metals can be brought into by two ways only. One through a bridge that we call the super exchange pathway, etc., etc., or through metal-metal bond. That is another way to do it. But the most of the materials what you see in a polynuclear setup, they are essentially through a kind of bridge. Okay, and if it is a mixed valence setup, now mixed valence actually originated out of an isovalent situation. Isovalent means in a polynuclear setup, all the metal ions are in the same oxidation state. And basically 99.99% cases, you will be seeing metals are in that is thermodynamically stable configuration. Okay. all the metals would be in identical oxidation state in a particular coordination situation under a broader picture of a larger molecule instead of a smaller mononuclear molecule, right? Now, that kind of molecule where you have all the metals in same oxidation state, we call it isovalent situation. But there are certain molecules in our nature, earth crust, or in our biological system, you will be seeing that metals are in different oxidation states. Now that is more challenging. Once you have metals in the different oxidation state, that means you have two potential barrier over there. Okay. So one in say N plus, other in say N plus 1 plus, or one is N plus, other part is N minus 1 plus. That means 2, 3, 3, 4, 4, 5, whatever it is. So one is, you can define it also. One is in the reducing state, other is in the oxidizing state, right? So you have created a potential barrier through your molecular structuring or designing. Okay, so that's why I said 99% cases you will have the isovalent situation under a polynuclear setup. Only few cases you will have that kind of situations. And if you have molecule of that sort, that means if you allow the necessary energy to pass through the molecule in the form of light or whatever it is, then you should expect to have a new kind of charge transfer transition from reduced metal to the oxidized metal ion, right? And then if you make a long chain of mixed valent metal centers, then you'll have a vectorial flow of electron along the bond. Okay, and that's the basis of molecular electronics, actually. Anyway, I'll not go deep inside of that. The huge literature is available. Those who are interested, they can understand it. Now, these mixed valence compounds are present in our biological setup, as I told you already. For example, that oxygen evolving center of photosystem 2, 4 manganese are there. Na? So at one point of time, there was a huge debate when the Nobel Prize, they are given the Nobel Prize, and twice they gave the Nobel Prize. Na? So this, what would be the 4 manganese oxidation state combination? 2, 3, 4, 4, 3, 2, all sort of jargons are there. And now it is more or less settled. Then if you see the cytochrome C oxidase, copper centers, copper 2, copper 1. If you see that iron sulfur proteins, again that mixed valence setup is there. So in biology, there are many such examples where you will have this kind of mixed valence situation. Now naturally, I said it, the naturally also, na? For example, our spinels, you have already read the spinels, na? Normal spinel, inverted spinel, or a mixed valence setup. Similarly, your Prussian blue, the first mixed valent compound was discovered in nature, that was the Prussian blue, or it's called the Berlin blue. That is essentially what it is being written, that iron 2, iron 3 derived from cluster system, very complicated cluster system. And, I think a few years back, triple century of mixed Prussian blue, it was celebrated. 300 years, more than 300 now. So there was a celebration. And in those days, if you look at you can check in the internet also, na? Beautiful blue color. And that was the color was used in those days for painting also. In 300 years back, you could imagine what kind of materials are available, right? And even today also, it is very important for variety of applications also. So that means the mixed valency, you understood that what mixed valency mean. Okay. Now, Those are the natural things, okay? But in your biological system, you have a mixed balance setup. In your, say Persian blue is there in the nature. All sort of things are fine. The problem is if you want to understand the biology, how protein functions in body, how cytochrome C functions over there. Okay, photosystem 2, how it functions, or iron sulfur protein, how it works out. Then you need to know the basic fundamentals. That is why the fundamental research is so important. Unless your fundamentals are strong, your pillars cannot be. It's like in a multi-storied building. If your pillars are not strong, then you could imagine the quality of your building. Na? Similarly, if your fundamentals are not strong enough, then in any direction you can publish certain things here and there, you can manage certain things here and there, but you cannot be the leader. Okay, because you cannot grow the way it is necessary to. So fundamentals. So from that point, you need to generate a molecule, a mixed valent molecule in your laboratory, so that you can understand how the electron transfer takes place. You can understand how the concept of electronic structural aspect at the mixed valence state could be extended to molecular electronic devices, could be extended to the understanding of electrons, complex electron transfer in our biological system involving metalloproteins and all sort of things. Because one cannot open the body and to examine how the electron transfer is happening. Na? Okay, so you have to do it at the laboratory level. Now, if you want to do at the laboratory level, okay, then you have to have the model compound. The first model compound, the mixed valent compound, was the Krustov. We know that very simple compound, the first compound. And later on, in I think 85, he got the Nobel Prize to understand the electron transfer behavior over here. Okay, this is the molecule which is a Nobel Prize winning molecule. Okay, so for example, the nitrosyl, what I talked about, nitrosyl was discovered 1900, early 1900 by Jorgensen. Okay, it was inorganic chemist who discovered the nitrosyl molecule. But the problem was, inorganic chemists, they don't understand the biology. Or biologists, they don't understand the inorganic chemistry. So he could not conceive the fact of the importance of nitrosyl in our biological system. Only a group of doctors, they realized that how nitrosyl is important in our biological processes, and they got the Nobel Prize. The physiology guys, they got the Nobel Prize in around 1990s, but not the inorganic chemist. It was the inorganic chemist who discovered the but they failed the bus. Okay, because of the lack of understanding of biology or application ability. But here it's a reverse one. Biologists, they proposed that these are the molecules are present, and most likely some kind of electron transfer is going on over there, and mostly some mixed valence setup, etc., etc. But they don't understand inorganic chemistry. And then the Taube and Cruz from Stanford University, they came up with the simple molecule. Look at this molecule, pyrazine-based diethyrium setup, and it is an isolated state. Okay, one is 2 state, one is 3 state, and it is 5 plus conductivity. Simple conductivity meter. If you measure the electrical conductivity, you will be getting 1:5, 500 something conductivity. Yeah? Ohm inverse, centimeter inverse with the unit. And here, if it is 1:5, and all the amine ligands, they are not charge carrying ligands, right? Neutral ligands. And if it is so, that means it has to be 2, 3, or it is 2, it is 3, because it is identical molecule. It doesn't matter which metal is 2, which metal is 3. Now, if it is so, then one could expect to have a charge transfer from here to here, right? And that indeed happening. I have not shown you where the charge transfer band. So that tells us a new kind of charge transfer transition. So far, we understand the charge transfer transition means metal to ligand or ligand to metal. MLCT, LMCT, that happens within the visible region, right? Any molecule, if you take metal complex based. But this kind of transition, which is called intervalence charge transfer transitions, via the mediation of the bridge. That means nothing happening through space. So the d orbitals and the p orbitals of the bridge, if they are close to each other energetically, then they would carry this electron or this charge from here to here to here to here through the appropriate molecular orbital overlapping. Appropriate overlapping means that energetically compatible, and also the shape-wise has to be compatible. Otherwise, there won't be any overlapping, right? This is a nice overlapping, nice wrapping actually. And then the electron transfer takes place. There, one question came up very, very clearly: the how effective and how strong this electronic coupling over here. Now, there are two questions. The one, if the electronic coupling is not very strong, then it can be considered as a localized situation. That at a particular instance, one could consider this metal in the +3, other metal in the +2, or the reverse fashion. So one could predict through experimental techniques. There are many techniques are available, which I am not going to discuss, but one could say that one is the oxidized form, other is the reduced form, and it is the very symmetrical structure, so you cannot differentiate between these two. But what you can differentiate, that one is in oxidized form, other is in the reduced form. Alternatively, if your electron transfer rate is very fast between the metal centers, then you cannot distinguish which one in the oxidized form, which one in the reduced form. And then mathematically, we can define, instead of 2, 3, 2.5, 2.5. This is our interpretation. Okay, this is how we try to understand. Essential meaning is the electron is essentially that unpaired electron over here, which is very rapidly shuttling between the two centers. That means electronic coupling is very, very strong. Am I clear? And that kind of material is very important from molecular electronic point of view. I only I'm trying to give you a very qualitative interpretation without going deep inside, that in a mixed valence situation, you have two possibilities. One is defined as your localized configuration, and that means that at a particular instant, you can define that this metal in this oxidation state and this metal in this oxidation state, one is in the reduced one, other in the oxidized one. So the electron transfer rate is not too fast. That means electronic coupling or communication between the two metals via the mediation of the bridge is not that fast. Okay. Other scenario is very fast electron transfer or communication, and there your system is called very, very rich system for molecular electronics. And after that, thousands of molecules people have tested. Few examples, even at the organic level. Look at the organic level. This is neutral, this is cationic, and this is intermediate radical. So that's called organic your mixed valence setup. Both way it is possible, and all these materials are very important from molecular electronics point of view. Anyway, so it is a very basic concept.
I have one question here.
Yeah.
What was the 0.5 thing here? I didn't understand.
What I said, that here you are saying 2 and 3. Total
Right.
oxidation state is 5, right? Because
Hmm.
5 plus is here.
Hmm.
Okay, now you can define this is 2, this is 3. You cannot
Hmm.
cut electron, na? Okay. So what we can say, if it is localized setup, then at a particular instance, you can imagine this is 3 and this is 2. If it is a very fast electron transfer between this and this, that means that one unpaired electron is shuttling between these two centers. This is at a very faster rate. Then how do you interpret it? We can imagine the fully delocalized situation, and for our understanding, we can say that half electron is here, half electron is here. Essentially, there is no difference between the two metal centers as far as their charge is concerned. Clear? You understood?
Sure, sure. And what exactly does this electron transfer rate depend on?
It depends on many factors. I will come back to it.
Okay, okay, okay.
Many factors. So let me answer you. It depends on the factor of what metal you have taken. All metals are not same. What oxidation state you are considering in terms of D5. Here it is D5, D6. You can also have D5, D4. You can also have any other combinations. You can think about in terms of high spin, low spin. You can think about in terms of the bridge. Bridge could be neutral, could be anionic. You can think about this ancillary ligand, which could be neutral, which could be anionic. You can think about the solvent polarity, your dielectric constants of the solvent. You can think about the temperature impact. You can think about the pressure impact. So I said in the beginning, it's a vast ocean. Okay, so you need not to go into that side. I'm just giving you certain information. You will see it slowly that now if you have a, bridge-based system where you can see the metals are in the isovalent situation, what we call the reduced form. Now, if you assume that both the metal ions are same, their conditions are same, that means the co-ligands are same, and under the circumstances, each metal could be oxidized by 1 electron each. So eventually you can have the oxidized form 3,3, right? So neutral and 2 electron oxidation 2 plus. But this oxidation process can take place simultaneously or via 1 electron oxidation process. If it happens, this 2 electron transfer process happens simultaneously, that means there is no communication between the two metal centers via the bridge. But if it happens through the intermediate mixed valence situation, that means 1 electron first over here, and then another 1 electron transfer at this center. So eventually 2 electron transfer. So 2 electron transfer can take place in two different ways. One is simultaneous 2 electron oxidation or 2 electron transfer process, could be the reduced one also, and other is 1 electron each. If 2 electron transfer takes place, at a time, that means there is no communication. That's a bogus system. You can throw it out. But if 2 electron transfer takes place in a sequential fashion, that means you are passing through the your mixed valence situation. And normally mixed valence situation is not a stable situation. You have to trap it in solution. Okay, and there are ways to trap it. But Krustave ion, that's why it got Nobel Prize in the beginning, because it's a stable form. Okay, very accidental discovery, but good discovery. Yeah. Anyway, here you can have this form, or you can have a delocalized form, the way I said in the previous slide. Now you can apply a little bit of thermodynamics, that if you consider the Kc means comproportionation equilibrium. If we consider, then intermediate form by reduced form into oxidized form. This is intermediate form by reduced form into oxidation form. That means you have E1, E2 that you could get through your electrochemistry experiment. So eventually, if you use this equation, delta GC, this into the Nernst equation, where delta E means E2 minus E1. Okay. And then you can have your Kc equal to 10 to the power delta E by, this is the Nernst equation, 0.059 volt. And it is very easy to calculate delta E by electrochemistry experiment, you can calculate. So you would be getting Kc value. Kc is, if it is very large or large, that means your intermediate is reasonably stable. If it is very large, it is quite stable. If it is too small, it is quite unstable, right? So that means the stability of this, or Kc, tells us how good or how effective as far as the electron transfer at the mixed valence state is concerned. For example, this molecule, if you take, you have taken the bridge, in one case pyrazine, then slight longer bridge, same nitrogen, monodentate nitrogen based, and further longer one. Look at the Kc is decreasing like anything. Here Kc is abruptly falls from this value to 20 and then slight falling over here. What does it mean? That means the electron transfer between the metal center, which is a function of the length of separation, metal-metal separation, not bond, metal-metal separation. If you separate them to a larger distance, that means the effect is or impact is reducing. That's not a good case. But if you have a smaller bridge, that means if the metal ions are closer to each other, you can expect to have better overlapping, orbital overlapping I'm talking about. And as a result, communication would be more effective. Okay. So now based on that, let us take few examples. Now what I said to you, without going deeper inside of the mixed balance aspect, I said that if you have a mixed valence compound in hand, we can figure it out by EPR, whether it's a delocalized setup or localized setup. That is the only concern we are trying to understand over here, instead of many other things involving mixed balancing. Now, what do I mean? Say N plus, metal N plus, bridge metal N plus, that is the isovalent situation. From there, you have generated metal N plus, bridge metal N plus 1 plus. That means say 2, 3, 3, 4, 4, 5, whatever it is. Okay. Now I said that if the system is localized, then at a particular instance, you can define that this metal under absolutely symmetric condition. If you take asymmetric condition, situation will be altogether different. Under absolutely symmetric condition, that means you cannot distinguish chemically the chemical environment of each metal. That means both the metals having the same chemical environment, but only difference is in one is N plus, other is N plus 1 plus. Now there are two situations out of this. One is a localized situation where you can define this one metal is in the reduced form, other metal is in the oxidized form. But if it is a delocalized situation, then at a particular instance, you cannot distinguish which one is oxidized, which one is in reduced form. You will see an average. And to explain the average situation schematically, we consider N plus 0.5, N plus 0.5. It's a schematic representation of the average situation. How do you do it? That is the question. Now, there are many ways one could answer it. And one should not answer based on one spectroscopic technique. And then the concept of reliability is questionable. So you need to take few experiments together. And if you can establish the fact that all the instrumental results, they are speaking in the same direction, not necessarily identically same. They are actually speaking, the trend is same. That is more than enough. Then you can have a better confidence about your data, about your interpretations. Anyway, we are not going into all the detailed discussion. Just look at the EPR. Now, see, this is one of the finest examples, in my opinion. If you look at this dimoly compound, which is breached by the pyrazine. This is somewhat, we can say that, Proust-Taube analogs, right? Now here, if you look at the moly, each moly having the same chemical environment. Am I right? 2 phosphine, 3 CO, 2 phosphine, 3 CO, 1 pyrazine. And here one metal in the 0 state, other metal in the 1 state. Now 0 state means D6 configuration moly, chromium, molybdenum, tungsten. So it is D6 configuration. And if you consider moly in 1, it is a D5 configuration. So it is second transition. So D6 means T2G6, low spin, no unpaired electron. Here, 1 unpaired electron is there. Now there are two options. If we consider this is localized situation, then what we should expect? We should expect that this part, one half would be completely silent as far as the EPR is concerned. That means unpaired electron is here. All sort of spectral profile would be dependent on this environment, not this environment, right? So we can expect that one half can represent the other half. So if you remember, I already discussed this issue, that moly having two isotopes, okay, and out of that 75% there is no I, 0. So you get one broad line, okay. We have not considered any your hyperfine due to nitrogen or other cases. We have only considered that metal based signal. Okay, if you consider the simple metal base, you get one line, strong line, because of 75% moly based isotope having no I, zero, that is I equal to 0, and 25% would be appeared on both sides. So this is the ideal situation. For a single moly based, if you consider mononuclear moly, already you have talked about earlier, then you would see that 74% would give you this, and 6 lines 5 by 2. So you would be getting 6 lines, 3 lines in one side, 3 lines in other side. Now here, if you count carefully, you are getting 11 lines. Okay, so if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines. If you get 11 lines, what does it mean? If your unpaired electron is associated with this moly only, that means one moly, then 5 by 2, then you should expect 6 lines like this. But you are getting 11 lines. It means that both the mollies are involved. That means 2 into 2 into 5 by 2 plus 1, total 11 lines. And all the 11 lines are being resolved over here. And that tells us that this localized description for this molecule is not correct, because this electron is essentially shuttling between the two centers. So at a particular instance, one could define it 0.5 and 0.5 instead of 0.1. And just for the sake of your understanding, I'm giving you the similar observation through IR. This is a very interesting compound because IR active sites are there, carbonyls are there, na? Carbonyls, very nicely IR active group, and which appears in an isolated region, all of you know, close to 2000 centimeter inverse, right? Now, if you consider localized situation, then you have this moly and this moly are not same electronically. Where this is D5, this is D6. So you can have this 3 CO meridionally. So 3 signals over there, and you can have 3 signals over there, over here, right? But if you consider they are identical, like in the initial case, moly 0, if you consider, that is how moly 0, you can get 3 absorption bands, because both the mollies are electronically identical. So the 3 band, that means half of the molecule could represent the next half, right? Now the oxidized one, that means 0, 1, here experimentally again we could see the 3 bands. This is one. 3 bands like the isovalent situation, only shifted. That is expected. Shifting because your oxidation state increases, so band is getting shifted. So in this situation, if it is a localized situation, then you should expect 3 for this one, 3 for this one, 6 bands. But what we could see, the only 3 absorption, like the starting one. Okay, that tells us, because again the shuttling is very fast, so you cannot distinguish between this center and this center, and as a result you get the 3 IR absorbing bands like the isovalent moly 0 situation. So if you put both the experiments together, and also the Kc value is very high Kc value, it tells us a delocalized situation instead of a localized. So EPR is a very characteristic situation to define the localized or delocalized situation in a mixed valent compound. Okay. Now, I think this is the last but one example. You look at the very simple molecule. Manganese 2, manganese 1. Low spin compound, manganese 2, your D5, 1 unpaired electron. Manganese 1 is D6, no unpaired electron. So here you have 1 unpaired electron, here is no unpaired electron. So it is mixed valence situation. So as a result, you could expect to have the shuttling of this electron between these two at a slower rate or at a faster rate. Slower rate means at a particular instant, that particular experiment, the EPR time scale is 10 to the power minus 8, right? Second, that time scale, EPR would see that slower rate at a particular instant that one manganese is carrying the unpaired electron. Now, if it is very faster electron transfer, then EPR time scale cannot distinguish between manganese 2 and manganese 1. It could see manganese 1.5, manganese 1.5. Now, manganese is a 5 by 2. If it is a localized on a particular metal center, you should expect 6 lines. But if both the centers like moly in the previous case, you should expect 11 lines. Now, this molecule at room temperature, it gives us 11 lines. You can check at 11 lines. But at low temperature, it gives us only 6 lines. 1, 2, 3, 4, 5, 6. This tells us one more factor over here. That means the electron transfer rate is a function of temperature for certain molecules. And we know that if you increase the rate, temperature, that means electron transfer rate would be faster compared to when you record it at lower temperature, where it would be slowed down. And that indeed being happening over here. With when the rate is faster, that means both the metal ions are involved, and that could be just through their isotopic pattern only. Without isotopic involvement, you cannot differentiate by EPR whether it is localized or delocalized. So once both the manganese are involved in carrying this unpaired electron in a shared form through this bridge, then both the manganese, the isotope I values are getting involved. So you get 11 line. But when you lower down the temperature, then it is being localized over here. So as a result, you get only 6 lines. So it's a fantastic example to understand through EPR that the temperature mediated localized or delocalized situation for a particular compound. That's fantastic. Last example. Here it is more of, I should say, I'm giving you the example from the EPR point of view. So certain other issues are there, don't bother about that. Here again, we can think about the spin configuration. As I said in the previous, two copper cases, spin configuration could be easily figured it out by EPR for the metal complexes having your redox active ligand. Okay, so you take this molecule. Without going deep inside of this molecule, one thing you know very clearly that there is a paraquinone setup. Am I right? And if you look at this is ACAC 2 means 2 minus, and this is naturally 1 minus then, so 3 minus, and then 2 minus over here, 1, this is phenolic OH, 1 minus, so it's a neutral compound, charge balance compound. And if you look at the quinones, now quinone, this paraquinone, like cisquinone, it can have the 2 minus possibility. It can have the fully oxidized quinone possibility. This is called catecholate form. This is called quinone form and intermediate radical form. Now we have one compound, the native compound. Look at, this is the ACAC, as I said. This is ACAC. This is your ligand is 2 minus state, that means fully reduced state ligand. Okay. And metal in the 3,3 state. And it's a triplet molecule. That means they are not coupled. Okay. Now this is the isovalent situation. So triplet molecule, you will have EPR for the triplet with the G half, this half field signal, and then G equal to 2 signal, etc., which I have not shown it here, but that is routine spectrum as far as our understanding is concerned. Now, if you reduce this molecule, you see that this is the electrochemistry. You need not to understand, but I am giving you the impression. This molecule is here. It can undergo 2 electron reduction and 2 electron oxidation. So we have tried to understand the electronic configuration, including spin and mixed valency at the redox states. So this is your native molecule. That is the isolated molecule, structurally characterized, etc., etc. And here, if you reduce this molecule, or if you inject 1 electron here and 1 electron here, then what will happen, since your bridge is already in the fully reduced form, bridge cannot reduce any further. ACAG cannot ever be reduced. ACAG is the absolutely redox inactive ligand. So which component can be reduced over here? Only metal then. So this cannot be reduced. This cannot be reduced. This is in the fully reduced state. So only metal can be reduced, because we know that ruthenium, if you consider, it can have 2, 3, 4, 3 stable oxidation states. Okay. So you have to bring inorganic chemistry into here. Then if you go for 1 metal reduction, then you have a mixed valence situation. And then another reduction, which I have not shown, then it will be 2, 2 again. 2, 2. Now 3, 2, 3, 3, 3, 2, 2, 2. And here it is the mixed valence. And the next one is the isovalent situation, but lower analog of the parent one, right? Now this mixed valence case, you get one EPR. And if you look at this EPR, is a typical metal-based anisotropic EPR. G value I have not shown, but it is 2.3, something like that. So that is not a problem. But if you go for oxidation, then you have 2 possibilities, because your ligands, the bridge is in the fully reduced state. So there are 2 oxidations. So bridge can be oxidized simultaneously, successively from dianionic to neutral via the radical intermediate. Or metal could be oxidized. So it could be 3,4 or 4,4. What you have observed, that on first electron oxidation, 1 electron oxidation, we are getting on radical based EPR. So this radical based EPR, how to interpret it? Now, if you have metal based oxidation, then it will be 3 and it will be 4. And ruthenium 4 means D4 configuration. And D4 configuration means it is a dimagnetic situation, that T2G would be splitted further and the 4 electrons would be paired up in the lower 2 orbitals. Okay. So you will have unpaired electrons over here. And if it is so, then you should have expected this kind of EPR, but you have not noticed so. You got a very clean radical signal. That does mean that metal-based oxidations are not taking place over here. So what could happen? That ligand can easily be oxidized because it is dianionic. It can come over here. Okay, that indeed happened. It is here. So now we have the conflict, like those copper cases. The conflict is, if you have a 3-spin situation, say 3, metal 3, 1 unpaired, metal 3, another unpaired, and bridge is there. Bridge may, you have the radical. So you can have the 3 situation. One situation is the pair neighboring coupling. Neighboring coupling means 1-2 coupling. This metal and this ligand would be coupled, and then unpaired electron would remain on the second metal side. Then you should expect metal-based EPR, but that you did not observe. Since you did not observe metal-based EPR, so this electronic configuration can be ruled out. But this EPR could be interpreted via the another concept, that instead of 1-2 coupling, if we consider 1-3 coupling, that means there are 2 metal-based unpaired electrons, they are coupled, leaving the unpaired spin on the intermediate bridge. That means these 3 would be coupled, leaving the unpaired spin over here, which is called 1-3 coupled, instead of natural 1-2 coupling. 1-2 coupling is the natural coupling from physics point of view. But here, the EPR suggests on radical spectrum, and radical spectrum cannot be interpreted by the 1-2 coupling, then you should have the anisotropic metal-based EPR. So radical spectrum could only be interpreted by the fact that 1-3 coupling instead of 1-2 coupling. Then the question comes, how come 1-3 coupling being preferred over here? And then you need to go back to the structure. The structure is fully puckered structure. And there one could back calculate that magnetic coupling between the neighboring center, metal and radical, which is not favored. On top of that, some kind of through space metal-metal interaction is being referred over here. So this is how EPR could help us to understand the complicated spin configuration in the polynuclear framework or in a smaller molecule like copper, what I have said. It's such a powerful technique, though it has certain drawbacks. It fails in certain places, we have already said, but one cannot live with the negative. Negativity is fine, maybe 2% negativity, 90-80% positivity. And what we have also said that, unlike NMR, EPR instrument is a little bit more sensitive, sampling is more sensitive, and how to design the experiment, that is also equally important to extract the best possible scenario as far as this particular technique is concerned. And more importantly, to interpret the electronic structures, all aspects, spin configurations, mixed balances, localized, delocalized, all sort of issues, one needs to be equally experienced about the fundamentals and about the literature. Then only you can help yourself in a better way. And more specifically, you cannot interpret your data just by looking at the EPR. You need to depend on, as I said in the beginning also, the simulation as well as DFT calculation. Without DFT calculation, you cannot reach to a point where you would be feeling very confident as far as your EPR interpretation is concerned. I think I am through. So this is how our syllabus was planned. Hopefully you have understood to a certain extent, and hopefully you will be benefited in due course of time. Now is the exam time. Tuesday your exam. So Harshavardhan would be in touch with the TA concern, and let's see how best we can move on, and wish you all the best. Enjoy. That's all.
Sure. Thank you so much, sir.
So any query, questions if you have? Hello?
It's fine, Professor. I was just wondering with this example, isn't the ligand too big here? Matlab, will the coupling happen? Like the
Oh,
metal.
strong coupled. Strongly coupled. It's not the question of the ligand overall size, it's the question of the orbital dispositions.
I
Okay.
see.
So how the orbitals are getting, the 2 points are there. I said repeatedly that one is the energy compatibility, okay, and how they are being disposed on each other. For example, you may have 20 classmates, and I'm sure that you don't have good intimacy with all 20s in an equal fashion, right? It depends on your temperament. And what you call at the molecular level, the temperament means the energy. Yeah. So energetically, it has to be compatible. Okay. Not only that, this is one of the important factors, energetically compatible, and also their shape. Okay. That how whether for example, pz and dx square minus y square, you have noticed in the copper case they cannot overlap. Na? The shape-wise compatibility, energy-wise compatibility, if these two match properly, then only you could expect to have reasonable better overlapping. Otherwise, not.
Sure, sir. Thank you so much.
Okay, all the best.